co-organizers, and I'll run part of this workshop this week, and Javad Mashregi will run the rest of it. So first of all, welcome to the workshop on manifold and graph-based learning. We're happy to have you guys here in person and online. So we'll start today with Professor Soheil Kolouri from Vanderbilt. So this morning and tomorrow morning, he's going to be giving a mini course on geometric deep learning or manifold learning. Excuse me. What? And so as we go through the talks, feel free to write your questions in the chat, or if you, for those of you online, you can unmute yourself. For those of you in the room, you can either ask them and I will pass them along to the speaker, or you can ask for the mic and I can just take it to you. So without further ado, I'll hand it over to Soheil for the first part of his mini course. Thanks.
Thank you so much, Keaton. Yes, hello everyone, and good morning. Thank you for attending the first talk in our four-part series on Wasserstein embeddings for geometric deep learning. It's unfortunate that I'm not there giving this talk in person. I had to change my plans last minute. I'm so sorry about that. But it's at least great that we can do this remotely. So the talk, as I mentioned, has 4 parts. The first part we are going to look into, it's going to be an overview of the geometric deep learning. And then the second part, which is going to be today, is going to be an overview of optimal transport and Wasserstein distances. And then tomorrow we are going to talk about Wasserstein embeddings and sliced Wasserstein embeddings and how they are connected to geometric deep learning and how we can use them for geometric deep learning. Okay. So deep learning has become a prevalent tool in many fields, and the progress doesn't seem to be slowing down. We all observed AlphaGo beating Elise et al. In 2016, the work by Google DeepMind, and you might have also had a chance to play with OpenAI's language model, GPT-3, which was released in 2020, and is also now used in the GitHub Copilot to assist us with coding. And in 2020, we heard the news of the big news in AI and ML was the breakthrough from DeepMind in predicting protein folding with AlphaFold. And this year, through OpenAI's DALL-E 2, we observed the unprecedented performance of these deep models for conditional generative modeling and generating imaginary scenes that were we believe that only humans are able to do things like this. So I specifically think that DALL-E from OpenAI, in particular, it shows us the pace of the field and also the progress that has been made in the field over the past few years. So here we are looking at trained model that is asked to generate a painting of a fox sitting in a field at sunrise in the style of Claude Monet. And on the left, you see the state of the art in 2021, which was DALL-E. And on the right, you see a state of the art in 2022. And in 1 year, you can visually see that we have made a lot of progress. And the fact that our deep models can generate something like this is quite impressive. Okay, but today we are going to talk about specifically about geometric deep learning. And this geometric deep learning is an idea that's a unifying mathematical view of a seemingly diverse field of deep learning. So we have graph neural networks, convolutional neural networks, deep sets, transformers, recurrent neural networks, and so on. And this recent movement of geometric deep learning is going towards unifying these into a more mathematically rigorous way. Okay. So today we're going to have an overview of this geometric deep learning field and see what is going on there. We are going to start by supervised learning, which is a very common learning setting in machine learning, one of the easier ones. And in supervised learning, the supervised learning at its core is a function estimation problem, right? From the observed input and output pairs. So if you have an input is the image of a cat, we would like to have a parametric model that generates the label cat for us, as opposed to if we send it an image dog, we would like it to generate label dog. Okay. So while the function estimation problem has been studied significantly, and it's not a new problem, it's an old problem that's very well studied, it's been mainly, the main results are in the low dimensional problems. And as we increase the dimensionality of the problem, we face the curse of dimensionality. Now, curse of dimensionality is a term that we hear a lot in machine learning, and it's a multi-aspect term. And here, when I'm using curse of dimensionality, I really mean like we require exponentially more samples to ensure an accurate estimation of the underlying function. Okay. So we are going to be in this setting that we have a trainable model. And for this trainable model, we are going to use a neural network. We are going to see how to generate such a neural network, or how to design or such architecture. And then we would like to be able to map the input to the labels. Okay. But geometric deep learning is all about what type of geometric priors can we leverage to lessen this effect of curse of dimensionality. So can we reduce the complexity of our hypothesis class, for example, to ensure better generalizability of our models? But what do we mean by geometric priors? Well, the signal of interest, which in this case is an image, for example, is defined on a domain that can have certain geometric structures. So here our domain is simply a grid, an n by n grid. And the signal, which was our image, is defined as a function that receives a point u on this. Yes, you see my mouse, hopefully. It gets a point on the domain u, and it generates the RGB values of corresponding to that point on the grid, or to that pixel. Okay. The structure of this domain is usually captured by a symmetry group. And in our example of images, for example, we might be interested in the 2D translation group. Okay. So if we would like to translate one pixel from U to GU, G being our, an element of our symmetry group, here 2D translation, then the symmetry group acts on a point in the domain, which in the space of signals, the group actions on the underlying domain omega is manifested through the so-called group representation, shown as rho G, which is, for translation, we can simply think about it as a matrix multiplication with a vectorized version of our image. Okay. That shifts our signal. And okay, so here we have rho G applied to our signal X is equal to, it's defined to be equal to X evaluated at G inverse of U. Okay. And so this structure of group, symmetry groups and group representations, we are going to come back to them over and over and see how they can help us in designing specific neural architectures. Okay. So let's see how we can use these geometric priors to lessen the complexity of our hypothesis class. For instance, let's say we are interested in models that are translation invariant. So what do we mean by that? If we would like to have a cat recognition, a cat-dog recognition model, the image recognition problem, in an image recognition problem, we would like this to be invariant to the translation. So the cat is a cat regardless of where it is in the image. So then we would like to enforce invariance to the 2D translation, the translation group for our images. Okay, so our model applied to the translated version of the signal is going to be, ideally is going to be equal to the model applied to the untranslated version of it. Okay, and that's exactly telling us that the cat is a cat, regardless of where it is in the image. Okay. But we can also have a case where the function has the same input and output structure, and we would like, if the input is translated, we would like the output to also be translated accordingly, right? So this is known as the equivariance. So for example, in semantic segmentation, where we would like to classify not the entire image, but we would like to classify each pixel in the image. We would like to be able to say this pixel is a cat, that pixel is a background, right? We would like the output to, or a semantic segmentation of the cat also move and be translated around as we are translating the image. Okay. So in such scenarios, we require our function to be a translation equivariant function. Okay. And okay, so if we are aware of what type of invariance and equivariance we need, we will be able to enforce these on our models by designing our model to satisfy these equivariant or invariant characteristics. And then the last part of like geometric priors that we commonly use in deep learning is the notion of a scale separation. Okay, so in a scale separation, we can consider a multi-scale hierarchy of domains. So here we have omega as our fine resolution domain, and we have omega tilde as our coarse version of the domain, or coarse resolution or domain. And then we can define the corresponding low resolution signal or coarse-grained version of our signal there. And we call a function to be, excuse me, we can define our function to be locally stable, or function f to be locally stable if we can approximate it as a composition of this coarse graining operator P with a model that's learned on the low resolution version of the image, or the coarse grained version of the image. Okay, so f theta is approximately equal to the f tilde, which is the coarse grained version of our model, applied composed with the coarse graining operator P. Okay. And by the way, this concept of multi-scale hierarchical domains has been very well studied in multi-resolution analysis of signals and in the signal processing community. For those of you who are familiar with those domains, this is not a novel idea. This has been used over and over again in the field of signal processing. Okay, but then these three principles, equivariance, invariance, and scale separation, will give us a blueprint to design many different types of deep neural network architectures. Let's see how. So we can essentially compose simple group equivariance layers. So let's say each one of these blue rectangles here is a group invariant operator, and we compose this group invariant operator to this simple group invariant operators to get a more complex group invariant operator, a composition of group invariant, group equivariant. Composition of group equivariant operators is also a group equivariant operation. And then if we want group invariance, we can simply use a global pooling approach, which is a group invariant operator here. For example, in the case of translation, we can think about global average pool or simply a sum. And then this group invariant operator aggregates the information into a fixed dimensional vector that can be used for downstream tasks like classification or regression. Okay. We can also bring in the idea of this hierarchical analysis of our models in our model and use a scale separation through a coarsening procedure. So what is this coarsening procedure? For example, if you're familiar with convolutional neural networks, we use local pooling mechanisms like local max pool. And the local max pool essentially reduces the dimension of the image, and it really works as a coarse graining operator for our model. So we can bring this idea of the scale separation into our blueprint. And this really is going to give us like more or less a roadmap of designing many different types of neural architectures. So if you are looking at a ResNet, residual neural network, for which are convolutional neural networks, we see immediately that there are equivariant operators through convolution. There are local pooling through, for example, max pool. And then eventually we have a global average pool that makes a group invariant or translation invariant in that case operation. And then like this whole function becomes a translation invariant function. Okay. Any questions so far? I'm not going too fast.
So Soheil, you have not, I believe you have not defined G invariant. You have defined the coarsening, the G equivariant, but I don't believe you defined the G invariant, although the G invariant is probably the first thing at the beginning.
Yeah, so here is the definition of G invariant.
Oh, okay, right? Sorry, I didn't see that. Yeah.
No worries, right. Yes, so we would like, F is group invariant if the representation of that group applied to the signal, if this is the translated image, for example.
Yeah. Yeah.
Then F of that is equal to F of X.
Excellent. Thank you.
Right. Yep, absolutely. Thank you, Akram.
A question. So it sounded like the sort of the motivation from this is to try and place constrictions on our network to reduce the cursive dimensionality. And in sort of the model architecture, you described sort of the strongest restriction, this invariance, only comes at the like very last layer when we do this global pooling. Is there an advantage to like having that invariance sort of enforced all the way along versus sort of sticking with equivariance and then only pooling to invariance?
That's a fantastic question. Okay, so that's a very good question. Let's go back to the mechanism that we have. So the question is like, why are we applying this group invariance at the end and not necessarily in the beginning? Okay, so I'll try my best answering this question. I have thought about this problem a lot. Okay, but this is just my personal view of the problem. So group invariance is not the only thing that we need, right? So if I, sorry, let me see. If I'm really in the business of doing supervised learning, a cat dog, I want to have a function that's a cat dog classifier, right? Of course, I want this to be group invariant, in this case, translation invariant. Right? But translation invariant is not the only thing. It's actually, that's not the main thing that I want. The main thing that I want is to be able to say, this is a cat, that's a dog, right? I can have a model that gives me a fixed output regardless of the input, and that's a translation invariant function, right? So I not only want translation invariance, but I also want a translation invariant that can separate these two classes, okay? And now separating these two classes is the interesting question. Like if we go to the input space, we know that we live in the images live in a very high dimensional space, but they live in a low dimensional structure in this very high dimensional space. And they can be significantly tangled, meaning that they might not even, if you have infinite number of images of cats and infinite number of images of dog, most likely a linear classifier won't be able to separate these in that high dimensional space. Okay, so we need a nonlinear operator, potentially a highly nonlinear operator, to disentangle these two, all images of cats from all images of the dogs. And on top of that, we would like the group invariance, right? Now, like, how do we gain that nonlinear function? Like, if we apply these group equivariant operators and we make them to be slightly nonlinear, when we compose them over and over and increase the depth of the network, this becomes a more and more nonlinear operator, right? And that nonlinear operator is tasked to separate the classes of cats and dogs while being equivariant. Okay, and then after that, we will be able to apply the invariance pool and then ensure that the whole thing is an invariant operator.
Gotcha. Yeah, thank you so much. That helps.
Yep. So, any more questions? Okay, if not, we can go and talk about convolutional neural networks as, I think, like the main advances in deep learning came from convolutional neural networks and around the 2011-2012 time period. So why do we have convolutional neural networks? Well, we know that convolution is the only linear translation equivariant operator, right? So if we want translation equivariance, we must use convolutions, right? And here we are looking at, of course, the formulation of the convolution, which we're all familiar with. But because it's a linear operator, composition of linear operators is not necessarily interesting, because the composition of linear operators is also a linear operator, right? So here we would like to be able to get, as I mentioned, we would like to get a nonlinear operator that's translation equivariant. So how do we build this? Well, we have this convolution, this translation equivariant operator, which is convolution, which is, and it's also linear. Then we can simply apply an element-wise nonlinearity on our convolution. So what do? We define this Fi that goes from our signals to signals. And this Fi is simply defined by a nonlinear function that goes from R to R. And this nonlinear operator here is, for example, a sigmoid function or a ReLU function. So, but the point is that this is applied to each element of our signal. So this is applied element-wise. And then when we define this element-wise nonlinearity, we can compose that with our convolution. And now we have a translation equivariant operator that's slightly nonlinear. Okay. And then if we apply this over and over, like we compose such functions together, we are going to become deeper and deeper. We will be able to generate highly nonlinear translation equivariant operators. And I'm using these terms very loosely. It's slightly nonlinear and highly nonlinear, but you can imagine that if you have, for example, a sigmoid, and then in early layers, you have less nonlinearity than in the deeper layers of your neural network. So, and then we can say this idea of convolutions as, I mean, we looked at convolution for the group of translation, and that's the classic convolution that we are familiar with. But we can also have group convolution that's defined on any group that we, on any symmetry group of interest that we have. And then we can essentially show that this group convolution is a group equivariant operator. So we talked about translation equivariant, but this is generally true for other types of group symmetry as well. And in a similar manner, we can define our Fi to be essentially a nonlinearity applied element-wise to the output of group convolution. And then we can compose these functions. Here it's a little bit of technicality that I'm kind of like brushing under the rug, and that is our signal is defined on our domain omega, but after we do this convolution, our domain is not omega any longer, or domain is G. Is the group symmetry domain. So now it happened that and when we're talking about translation, the group is the similar as our domain, right? But if you're talking about group convolution, only the first function is going to have its domain equal to the domain of X. The other functions have their domains be equal to the group domain, the group symmetry. Okay. So, but nevertheless, we can essentially generate a G equivariant operator by composing these simple group equivariant operators back to back and generate a more complex group equivariant operator. Okay. Excuse me. Okay, so far we've been talking about grids and signals supported on grids, specifically images, right? And such signals are prevalent, right? Like we can talk about the speech signal, images, videos, they are all defined on different types of grids. But there are a huge family of other types of data that are not defined on grids, okay? So they are not defined on necessarily regular domains like grid-like structures, but they are defined on graph-like structures, right? So, for example, we can think about social networks, we can think about point clouds, we can think about communication systems and molecules, and these all can be modeled as having a graph domain, and the signal is defined on the graph. So signal supported on irregular domains or signal supported on graph. Some applications include molecular graphs. It's a very hot topic right now. Deep learning on molecules, as I mentioned, for example, AlphaFold. AlphaFold's success in predicting the protein folding, or we can think about drug discovery. If we have a model that can tell us whether a molecule is likely to cure a certain disease or not, then such model needs to receive a molecule in the input and outputs a score for us. So how can we do that? And this is a very hot topic currently. In pose graphs in computer vision, for example, we can have we can model different poses of a person as a graph and then do analysis on this graph. Or in social network, we of course have gigantic graphs where each node is a person and their preferences and so on, right? And the edges show, for example, friendships. Okay. So let's look at a signal that's defined in a graph and set some notations that we would like to have. So we're going to define a graph through its edges, through its nodes and edges. And then we are going to say each node can have an associated signal, which is our node feature. We are calling it here node feature. So xi is the feature for node I. And if two nodes share an edge, then there's an edge ij between them. So we can essentially represent this graph as an adjacency matrix, which is telling us which node is connected to which node. Okay, so it's an n by n matrix where n is the number of nodes that we have. And we can have a feature matrix, which is essentially the signal that's defined on this graph. Okay, so something that's particularly interesting in, excuse me, in graphs is that the indices of these nodes is quite arbitrary. right? So here, for example, we have one set of indices. This is node 1, 2, 3, 4, and so on. And we have the associated adjacency for node 1. We see that node 1 is connected to 2 and 3 and 5 and 8. And then there is a corresponding feature for that node. But we could have had a different set of indices, and we could have called that node node 2. Nothing has changed. This is still the same graph, the same signal defined on this graph, although now our adjacency matrix completely changes, and similarly our feature matrix changes as well. How do they change? They change through a permutation, right? A permutation matrix P applied to our A. So PA, P transpose is going to be our new adjacency matrix, and PX is going to be our permuted features. And of course, we can have n factorial permutations on this graph. Okay, so if we want to learn a model if we want to learn a model that can get this signal that's defined on this graph and gives us an output, what can we do? So let's say we are in a graph classification and regression problem. We have a molecule. We are representing this molecule as a graph. This graph has an adjacency matrix, has features associated with it. And we would like to learn that function f theta such that it's going to tell us whether this molecule is toxic or non-toxic for humans. Right. So we immediately see that this model must be permutation invariant. Why? Because as we said, there are n factorial ways that we can define the same graph just by arbitrary indexing it differently. And we would like all of those to lead to the same answer. So here, the important point is permutation invariance for graph classification and regression. In other applications, like in social networks, for example, we might want to classify the nodes, or we would like to essentially predict the preferences of different users. And in that case, we would like the output to, if you're permuting the input, we would like the output to be permuted as well. Say if this is the preference for a person index 1 here, if we permute this graph that we have, and now what we were calling person 1 now has become person 6. Of course, we would like the preference of that person to be permuted as well, right? So we don't want to associate the preferences of a different person to the person we had here. So in this case, we really like to have permutation equivariance for node classification or node regression. So graph classification regression, we would like permutation invariance. Node classification and regression, we would like permutation equivariance network. So then, following very much the same blueprint that we had before, we can design a neural network that can be applied on graphs. So here we are talking about graph neural networks. And we know that we require to have permutation equivariant operators, and we would like to compose these permutation equivariant operators to generate a more complex permutation equivariant operator. And then if we require permutation invariance, we can apply it at the end. And if we would like to have this coarsening operator or scale separation, we can even have that for graphs as well, right? And we see that immediately the only thing that has changed from this new type of graph structured domains as opposed to the grid structured domains, the thing that has changed is simply the symmetry of interest, which is permutation versus translation in that case. So any questions before I move on to define the permutation equivariant operators used for graphs? Okay, if not, I'm going to move on. So let's construct a broad class of tractable functions to be permutation equivariant. Okay, so generally we can for each node I, we can define the neighbors, the set of neighbors. Here we are showing it at Ni, neighbors of node I, and those neighbors are the ones that share edges to our node I. And then we can define or a local aggregation function h of, a local aggregation function h of theta. That's going to be a function, a parametric function of our self features xi and our neighbors features x and I. However, if we really want to get the equivariance that we need, we would like to generate a equivariant operator here. We want to ensure that this function h theta is invariant to the permutation of the neighbors. Okay, so let's say if this phi of theta of xi and xni is equal to phi of theta of xi and the permuted version of the neighbor nodes. So if our indices were different and our neighboring nodes were permuted, we would like to get the same output. Okay, so we would like this h theta to be permutation invariant. Okay, then if we apply this h theta to all our nodes, so h theta of x1 through h theta of xn, this is going to give us a function f theta on our entire graph x and a. And this function is going to now be permutation equivariant. Okay, so this f theta of px, pa, pt, p transpose is going to be equal to the p of f theta and xa. Okay, it's very easy to confirm this. And so this gives us a general way of designing functions that are permutation equivariant on our graph. And interestingly, when this phi theta is injective, one can show that the resulting neural network by composition of these is going to become equivalent to the Weisfeller-Lemon graph isomorphism test. Okay, so we are going to see that in a moment. But what is graph isomorphism? Graph isomorphism is if there exists a permutation matrix P, that the P transpose, essentially the permuted version of that graph, is equal to another graph. So then these two graphs are isomorphic. So it's just a different representation of the same graph. And we would like to be able to say these two graphs are the same. Okay. But what is this Weisfeller-Lemon test? It's a necessary but not sufficient condition for graph isomorphism. And it's actually going to be the gate to the Wasserstein, the use of Wasserstein and Wasserstein embeddings for us. So this is an important point of the talk. So let's say we have a graph with 5 nodes. And here gray is, the color gray is showing the feature that we have. And now we do our local aggregation, the phi functions that we talked about. So here, the local aggregation for this node is going to be the self is gray, and it has 2 neighbors, and each of those 2 neighbors are also gray. And then this function is going to assign color yellow. And we can confirm that the same thing is happening for this one. It has 2 neighbors with gray color, and then itself is gray, so it's going to be assigned with color yellow. And so these 2 nodes are a little different, right? So they have 3 neighbors, three gray neighbors, and then we are going to assign a different color to them, blue. And then if we repeat this this process one more time, now we see that our blue points or blue nodes are going to have 1 blue neighbor and 2 yellow neighbors. So we are going to assign color red to that. And then this yellow point is going to have 2 blue neighbors, and we are going to assign color purple to that. And then these 2 are going to have 1 yellow and 1 blue neighbor, and we're going to assign color green to that. And then if we repeat it one more time, we see that nothing changes, meaning that the colors are going to essentially be the distribution of the colors is not going to change any longer. So we are finished in that case. And then we look at the output distribution, which is the distribution of the colors for this graph. So we see we have 2 red nodes, 2 green nodes, and 1 purple node. So if we do the same thing for an isomorphic graph, we see that we eventually reach the same color distribution. And now if we compare these 2 color distribution, these 2 output distributions, we see that they are the same. And so there is a possibility that these are isomorphic. Again, this is a necessary but not sufficient condition. Okay, so this is the Weisfeller-Lemon test. And we can immediately see that there is a notion of comparison of distributions here. And this is where we're going. With optimal transport, we are going to be able to compare these distributions effectively. And that's where we go. Okay, so just to be a little bit more precise and clarify some of these ideas of the aggregations or local aggregation of messages on the graph, we can define a generic formula for these local aggregations, these H thetas that we define. And this generic aggregation could be done through a process called message passing. Okay, so what do we mean by message passing? In each layer of our neural network, we have our phi, which is a learnable function, depend on xi, node features for node I. And this is a permutation invariant aggregation operator, for example, sum. Okay. And we have this permutation invariant aggregation of some function psi that's a function of xj and xi. Okay, so and by the different choices of this psi and this phi, you can come up with many, many different graph neural networks. And some are more interesting. They're more, they're easier to train. They have like more favorable characteristics and than the others. For example, a popular and a very common variation is to essentially decompose this psi into 2 parts. That one has an attention that calculates an attention between xi and xj. This can be simply like a cosine similarity or something like that. Applied with a psi of xj, and this psi of xj, for example, can be a multi-layer perceptron that's applied to your xj. So this is a nonlinear but learnable function that we can train. And then these h thetas are going to define our message passing layer, right? So there are messages being passed between each node and its neighbors through this operation, and then we aggregate the information from the node and all the neighboring nodes and apply another nonlinear function to define a permutation equivariant operator. Okay, and we see that in various graph neural networks, as I mentioned, and we see that different layers are doing the message passing, and at the end we have a permutation invariant operator, which is, for example, a global average pool. Okay. And by the way, like an interesting point here is that each layer of our graph neural network is aggregating information from the neighbors to the center node. So essentially, when we go 2 layers deep, the information from neighbors of neighbors reach our center node. So the deeper we go, the information that a node aggregates comes from further and further neighbors. Okay, so that's also an interesting and important point. Okay, but so we saw graphs, and then another interesting type of data is sets data, and learning from sets has become a very hot topic in machine learning and specifically deep learning. There are many applications to learning from sets. For example, we can have point clouds that we would like to classify and so on. But we can immediately appreciate that a set could be thought as essentially a graph without edges. Or alternatively, because there's no information in the edges, right? Alternatively, we can think of a set as a graph a fully connected graph, a graph that has all the edges. So depending on the type of problem that we would like to do, if we would like to have a set classification and regression, very much similar to graphs, we have a permutation invariant group that we would like to have. And if we would like to set element classification and regression, we need a permutation equivariant operator. As I mentioned, there is no information in the edges when we are working with sets, so we can really think about them as graph with no edges or graphs that are fully connected, one or the other. And interestingly, if we think about graphs, fully connected graphs, and we write our local aggregation message passing operation through attention, we immediately see that we are going to recover the transformer architectures that are very, very hot and common these days in deep learning. And so I mentioned point clouds, and for LiDAR data specifically, you receive point clouds, and you would like to learn on these point clouds. And for example, you might want to classify what this point cloud is. This is a mug, this is a table, this is a car. So this is a set classification problem. You may want to do part segmentation. Here you need permutation equivariance, because this is a signal defined, and you would like to be able to classify each individual point, very much similar to the semantic segmentation that we had on our images. And likely there are two different types of segmentation: semantic segmentation and part segmentation. And there are very interesting data sets out there, like PointNet data sets, that allow us that have all these, if you're interested. So I'm going to wrap up. We mentioned, we looked at this permutation equivariant operator a lot, right, during this talk, but we really didn't focus much on what is this permutation invariance operator. It's very common to use global sum or average pooling in deep neural networks. But if we are going with the Weisfeller-Levin test, we know that we need to look at the distribution of these points, these colors that we looked at. And really taking an average of these distributions is going to cost us some expressivity, right? Like, so we are not going to be able to express the entire distribution. We're going to rely only on the first moment of our distribution if you're using a global average pool, for example. And it discards all the information about the distribution. And one question we can ask here immediately is, can we do any better? And of course, it is just a visualization of what's happening when we do our permutation equivariant operator. We have these distributions in a d-dimensional space, which is the node embedding that we have. And we are really doing, by global average pooling, we are looking at the average of these distributions. And that gives us a fixed dimensional representation. And we can have, of course, downstream classification and regression on it. But if we want to be a little bit more rigorous, maybe we would like to actually look at the distributions and compare these distributions, and how can we do that? And we are going to see that optimal transport is going to be a very interesting and very powerful tool that allow us to do that. I'm sorry. Okay, so that's it. If you have any questions, I'll be happy to answer.
I have a quick question, Soheil, just for the last, yeah. So, okay, so you want to change your, the average to an embedding, and you're saying that's this new change now. You'll explain that, or?
Yes, yes. So that's the next part of the talk. So in the next part of, actually, that's going to be the entire goal of the talk, right? The 4 series that we have here. What we are saying is, as opposed to getting the average and then use this average to do learning on these graphs,
right?
About comparing these 2 averages. Of course, if our distributions are exactly the same, these averages are going to be the same. So the Weisfeller-Levin there is true. but we can have distributions that look very different from each other and have yet they have the same average, right? And then that's essentially telling us that this average, Weisfeller-Lemon was going to tell us that these two graphs are not isomorphic, but the averages are going to tell us that they're possibly isomorphic, right? And so we are losing that information. And now I'm going to talk about what can we do not to use this, lose this information. And the idea is we need to really compare the distributions together. Okay.
Right.
How do we compare the distributions together? We can use optimal transport and Wasserstein distances. But then the next part of the talk is what is optimal transport? How can that give us this of the distributions? And then we will reach at the point that using optimal transport is going to be too expensive for learning from graphs. And then what can we do is the Wasserstein embedding, which is the idea of linear optimal transport, and also a sliced Wasserstein embedding, which is similar to the idea of the array down CDT, essentially.
So what I mean, okay, so basically you wanted to learn the distribution. There is also probably somewhere in the middle, I mean, where you can learn the moments, so up to a certain moment, number of moments, right, for the distribution.
Right. So here, like, yes, instead of doing the average, the next better thing, the next best thing is to go and, for example, calculate some covariance of these and compare the means and covariances.
Exactly.
So any distance is fine here. I'm not. The point is, if you use any distribution distance, it's going to be better than just relying on the first moment, right?
Right.
The best is if you can use all the moments, right?
That's right. Exactly. Yeah. Okay.
And optimal transport will allow us to essentially compare this distribution more accurately, right? Like not just first, second moment, as essentially like infinite moments of
right.
Space.
Thank you.
Absolutely. Thank you.
Is it invariant to increasing dimensions also?
Can you repeat the question? I'm not sure if I understand.
Is the method, like the average thing, is it invariant to increasing dimensions, data dimension?
Increasing to data dimension. Right. So I mean, like these distributions can be defined in any dimension, right? So
yeah.
This node embedding is getting a graph, and it's essentially embedding this graph into an n by d matrix, and n being the number of nodes and d being the dimension, and that d is a choice that we have in designing the architecture. We can increase that d as much as we want, right?
Okay.
Yes, but yeah, the invariant, this global average pooling is on that n, so it's going to give us a d-dimensional vector.
Okay, thank you.
Any other questions?
Yeah, this might be a question that you'll answer in the next 3 parts of the talk, but Wasserstein distances and optimal transport are sort of fundamentally about like distance between 2 distributions,
right?
Which seems like sort of a very different thing than like a global pooling or these moments, which are sort of fundamentally about a single distribution that then you can compare if you want to. And I'm just wondering how you can sort of use this Wasserstein distance to sort of get that sort of single distribution statistic.
Fantastic question. Thank you for asking it. Right, so you're absolutely right. Wasserstein distance is a distance. It's going to get 2 distributions and give us their distance, right? But it seems like this group invariant pooling that we have gets 1 distribution, and it gives us a fixed dimensional representation for that, right? So we are going to answer this in the next 3 parts, but I can give you the short answer now. If we are using the Wasserstein distance, you're absolutely right. Like, we're required to do pairwise comparison, and this paper that I'm showing here, which is not by us, by our group, Wasserstein, Weisfeller-Lemon graph kernels, it's a NeurIPS 2019 paper. It actually does this pairwise comparison and uses kernel methods. You have the similarities between your pairwise graphs, and then you can use any kernel method of interest, like kernel SVM or kernel SVR, to do machine learning on graphs, right? But we don't want to do this. What we really want to do is to have something that actually embeds a distribution into a vector such that the distances between these vectors, the Euclidean distances between these vectors, is approximating the Wasserstein distance between their corresponding distributions. So we would like to have an operator that gets a distribution and it outputs a fixed vector, which is exactly like the group invariant operator that we have, like a pooling, global pooling. And then we would like to, the outputs, these vectors, to be in a way that the Euclidean distance between them approximate the Wasserstein distance. And that's why we are going to call this the Wasserstein embedding. Right. Does that answer your question?
Absolutely. That sounds very exciting. I'm interested to hear it. So thank you.
Okay, so I think we'll take a short break until the second part of Soheil's mini course. So we have about maybe 6 minutes and then we'll come back. Thanks.